Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this news briefing from ACS Spring 2021. We are joined today by Dr. Marcus Buehler from the Massachusetts Institute of Technology. He is making music from spider webs. Dr. Buehler.
Hi, Sophie. Thank you for having me today, and nice to meet you all. Nice to see you all today. What I'll do, I'll talk a little bit about the paper I'll be presenting actually later today on turning a spider web into a musical instrument and using visualization and virtual reality to understand the construction principles of spider webs better. As you can see here on the title slide, this is collaborative work with my PhD student, Isabel Su, who just graduated, Tomás Saracino, my collaborator in Berlin and Argentina, and Ivan Cipirin at MIT, whom we worked with to transform these thousands of silk threads into a musical instrument. Next slide, please. So as you can see on the very left, on the bottom, we begin by looking at a spider. And spiders, as we all know, build spider webs. Now, most of us are familiar with the two-dimensional spider webs, the orb webs, which are basically these spirals that you would draw if I would ask you to draw a spider web. But it turns out that most spiders that live in this world actually build three-dimensional spider webs. And those are seen on the image a little bit above the spider. So those are the kinds of spider webs that most spiders build, and these are commonly also referred to as cobwebs. And what we have done is we have developed a method together with Tomás Saracino and our collaborators to scan these webs using lasers and assemble these thousands of images that we have taken off these webs from different angles, by lighting up different sections of the web, into a three-dimensional model. And this is the work by my former PhD student, Isabel Su, who created this technology to automatically process these images and transform them through image processing software into a three-dimensional model, which you can see a little bit to the right. Now, why are we interested in looking at spider webs? Well, there are many reasons. One is that spiders are really interesting, really interesting 3D printers. They are autonomous 3D printers that essentially construct spider webs like a 3D printer, but without any support material, without any scaffolding material. So that's quite a feat. Also, these spider silk threads are very strong and very tough. They actually rival the strength of steel. And so we have a material that is created or spun by the spider in real time with very low energy consumption, creating these very complex structures in three-dimensional space that we're trying to understand better as scientists, or maybe even build synthetic spider webs or synthetic structures inspired by spider webs as engineers. Next slide, please. So when we look at these spider webs, this here is a projection of the entire three-dimensional spider web onto a two-dimensional plane. You can see thousands of these individual strings or segments of strings. And this sort of composite structure reminded us, of course, of a harp instrument or a string instrument. Now, what's interesting here is that you can imagine each of these little bits of strings can vibrate. And actually, the spider uses these vibrations during the operation of the web. Spiders, of course, use the web for prey catching, but also use the web as a collector of information, of sensory information like vibrations. We can imagine this being a source of musical sounds by transposing these frequencies into the audible spectrum. And so once we take a look at this three-dimensional structure, you can see that you can imagine this being an instrument you can interact with. So what my student Isabel did is she created a virtual reality environment in which we can actually enter the web virtually and wander around the web structure. And then we use physics-based simulations to calculate how these individual string segments would actually vibrate, and we can make them audible. And so what we can imagine now is playing a little bit like being a spider and wandering around the web and playing with the web just like we would pluck on a harp or guitar string or violin string. But in this case, we're of course using the real spider web to do that. And so the sounds that we've generated here are quite interesting. They don't sound like conventionally tuned instruments because, of course, a spider does not use the type of tuning system we use in musical creation. But rather the spider has tuned the web to their own idea of how the web should be tuned as an optimal sensor, optimal prey catching apparatus. Next slide, please. So this shows a little bit of the principle behind that. So on the left hand side, I have two images. One is a movie. The bottom part of the movie is actually a conventional guitar string in slow motion, and you can see when you pluck the strings, they vibrate and they form these wave patterns, which is what we hear in our ears as sound. On the top is a 3D printed version of the spiderweb, just to illustrate these segments of strings. And so you can imagine now when you play this kind of instrument, the sounds are going to be very complex. They're not going to be as conventional instruments sound like. So we've developed this instrument into something we can play either virtually on a computer. We've also had performances. This was done with our collaborator Ivan Sapirin and his team, where we had Isabelle Su playing the spider on stage, the spiderweb on stage with other human players playing human instruments. And we can also do this, of course, in videos. And so we have a bunch of videos on YouTube where you can watch this instrument being played. We've done many other experiments. We have looked at how the sounds will change as you stretch the web. So when you take a spider web and you pull it and you break it, you can hear the snapping of the individual strings. You can begin to hear the pitches increase, just like when you tune a guitar, you increase the tensions, because the spiderweb instrument, of course, is based on physical principles by which strings work. And so when you increase the tension, the sound will change. On the right-hand side, you see a photo of Isabella on the right, and on the left-hand side, you see another student who has been working on this with a group of students over the years. We have done some really, really interesting work. Left-hand side is Nyosha, an undergrad student right now at MIT. And Isabel and Nyosha and other students in the lab have created this method of scanning the webs and created many different kinds of models. So tonight in the presentation, I'll talk a lot more in detail on how spider silk is made from proteins, which is, of course, of great interest to the American Chemical Society. We study proteins for many different applications. Here we look at proteins as a structural material to create spider webs and then analyze the spider web as a new source of musical instruments, but also developing new kinds of 3D printing technologies, and also creating virtual reality environments by which we can create what's called digital twins of these spider webs. So I'm happy to answer any questions you might have.
Thank you.
Yeah, so in your background, you hear a little bit of the spider silk music. While we're waiting for the questions, you can take a few seconds.
Give that just a moment to play out. All right, so at this point, I would like to ask if there are any questions from viewers. If so, please state your name and affiliation in the chat window when you ask your question. While we wait for those other questions to come in, I have a few of my own. First of all, what gave you the idea to turn spider webs into music?
Yeah, so we've been working on proteins and molecules and the way they move for a long time in my lab. And one of the things that you notice when you study molecules in general, but really anything in nature, it's always moving and vibrating, right? So the world isn't static. You can actually see this if you look outside, the wind's blowing on the leaves and they're moving and vibrating. And if you look at the nanoscale, the individual molecules, again, you can see them vibrating. And so we've always thought that these vibrations we find in nature could be a really interesting source for creating sound or music, and providing a complement or an alternative potentially to the way we conventionally come up with sound generation, which is really using macroscopic strings, tuning them and then plucking them. So nature has sort of its own orchestra of sounds available that we can utilize. And through the studies of spider webs with Tomas and others over the years, we have developed some really accurate models of these webs under different conditions like construction, stretching them, as I mentioned. And so we're thinking about we're thinking that these webs really looked literally like a harp almost, right? Because you can see the individual connections. And we also know, of course, that spiders utilize vibrations as a way to communicate with the environment, to communicate with other spiders. And some other work that has stimulated this actually was that we have recorded these vibrations from spiders and used artificial intelligence to learn these vibrational patterns and associate them with certain actions, basically learning the spider's language. So this sort of led us into the thinking of maybe using this literally as an instrument. And once we tried that, we found that the spider web is quite haunting. You were mentioning quite haunting in its sounds. Unusual, but also quite beautiful. If you listen to the sounds and you spend a little bit of time to listen to the evolution of the structural sounds, it can be appreciated. And so we have sort of attempted to being able to live a little bit like the spider or experience the world as the spider does in that way. And this has been quite a fascinating experiment to try.
All right. What species of spiders have you studied? And do different species produce different web designs, which could therefore result in different musical compositions?
Right. Yeah. So we have looked at many different kinds of spiders. One of the one that you heard here was the Certophila spider, but we've looked at many different kinds. Usually, we pick the spiders that build a beautiful big 3D web, so we can scan them. But yeah, in the lab we have looked at many different kinds of spiders, and different spiders, of course, build slightly different webs, which result in different sounds. And one of the things I'll also show tonight is some new work where we have observed one of those spiders build a web and sonified, and basically created a harp for each construction stage, so you can begin to see how the spider harp actually changes during the construction. So you have almost like a living musical instrument. It's not a static instrument. It's growing, it's adapting. And ultimately the dream or the vision we have of this is to being able to actually use a real spider as a way of creating vibrations, essentially capturing the motions of the spider and how she excites the web, to being able to play that on stage. We haven't been able to do that directly live yet. So we basically use a human player. We as humans move around the web and excite the strings and thereby make the sound. But ultimately, we could imagine also having a real spider perform with us on stage. This would be quite exciting.
How did you assign different musical notes to the web strands?
Yeah, so the basis for this sonification, and also a lot of the other work we've been doing over the years on sonification of proteins and molecules, is we use the real physics or chemistry or quantum mechanics of the motions. In this case, we're dealing with basically a string. So we use basically physics equations that relate the tension in the string, the length of the string to the frequency at which it will vibrate. So that's the same equation you can use to model a guitar string or violin string or strings in a piano. And so each string essentially has its own equation associated with it, whereby the geometry of the string, the length and tension, and so on, and the properties of the silk determine the frequencies, and then the aggregate of these thousands of different fibers in the entire web, create the sound that you've heard. Now, the sound you heard in this piece actually is created by moving around the web. So we're not exciting all the strings all the time, just like in a real harp. You wouldn't pluck all the strings at the same time, or in a piano, sounds pretty terrible if you hit all the keys at the same time. So what we do is we move around the web and only excite a couple of strings at a time. Thereby we can identify different regions of the web and how they sound like. So there's some regions that are very dense, there are regions that are very porous, the regions that have a regular structure, and each of them have a unique sound associated with them. So that makes this instrument playable in that way. And we can explore different regions of the web to create certain sounds that we like to generate.
And so I noticed that the music wasn't discordant at any point. Was that intentional, or was that luck, or?
Well, no, it's a great question. I think it is, maybe I wouldn't say luck, but there are some dissonances clearly in there. I mean, the frequencies that you heard are not frequencies necessarily that fall on a conventional tuning system, which really deals with very discrete frequencies like equal temporal tuning. So you're going to have, in any web, you're going to have a continuum of frequencies. But I will actually also show this tonight in the talk. I will go through an example of actually playing some white noise, which is basically completely random frequencies that creates basically noise, like water running in a faucet, or maybe a river. That's sort of similar to white noise. And so the web is not like that, right? It's not completely random. There are some structures in there, but there are definitely some dissonances in there. But as you play the web, you'll be able to use certain regions of the web that sound more pleasant and more harmonic than others. And when we do create music from this, that's an element that we utilize. We go to regions of the web that are maybe more disorganized, more random, and there's some regions that are more organized, more harmonic. And sometimes you'll actually are lucky to find certain harmonies in the web as well. And that's something, of course, when you as a human player listen to the web and you explore the web and you kind of look at different combinations of strings you want to excite, those are the kinds of things you can begin to introduce to the audience. and play something much more familiar, right, than the more random amorphous structures in there. So that's something that we can utilize. Yeah, but it is quite fascinating that there are some really interesting melodies in there, and we've developed an algorithm too to actually map the all the frequencies and basically snap them or match them to the closest nearest key, if you wish, on a piano, the equal temperament equivalent to that, and we can extract then melodies. You could write them as a musical score and play them, on a piano and a guitar. And when you do that, you can essentially utilize the spiderweb as a way of extracting new melodies, new rhythms that you can then use for other compositions. So there's a lot of really room for creative expression once you accept that the melodies might not come from a human, might come from a spider or a spider web, but it creates really very great inspiration for us to explore other things with it.
So I can picture somebody doing sampling with this,
right.
Taking snippets. Yeah.
Right. Exactly. So exactly, you can do. I mean, definitely, one can do that. One can, sample it and play it at different frequencies. You might get some interesting effects there. You can stretch it, compress it, and things like this. You can use some beat with it, and people can try all sorts of things. And what we have done in our lab, what I've done from the sounds, we have used a method called granular synthesis, which is a little bit like sampling, but it's using small grains of the web. So essentially, we're using small elements of the sounds and reassembling them, and that allows us to create essentially a new instrument out of the other instrument. And what you can do with this method is you can then put these little grains of sounds together at the right tuning and an equal temperament tuning, for instance. So basically, make them compatible with other human instruments. And we found that to be a very effective way of retaining some of the characteristics of the sound you just heard, but allowing it to play with other instruments like classical instruments or violin, and it gets quite beautiful. So you kind of have a really interesting continuum then available for sounds that are not completely synthetics. And you can make any sound, of course, using synthesis methods, but they're not based on any physics most of the time. But here you have a way of creating some really interesting sounds that are based on some a real object, a real living object like a spider web. So that's sort of the excitement that we have with this, is that we can create, we call it bio-inspired music in some ways, to talk to nature in a different way.
How is your harp-like instrument different from a conventional harp?
Yeah, I think the main difference is really that conventional harp will be tuned nicely. So you'll have certain basic bass notes that are, many of which are compatible, that we play together and sound harmonic, right? That's the basis for a lot of the tunings and harps and guitars and other instruments like this. Whereas the spider harp is not tuned for that purpose, right? It's not tuned to sound beautiful or nice or pleasant to the human ear. It's actually tuned for the spider to be an effective prey catcher or an effective, medium to collect information about the environment, about the wind loading, whether the web is intact. The spider is essentially blind, right? So it will use the spider web as a way of localizing prey. If there are other spiders nearby or maybe live in the web, there's some social spiders that live in colonies, if you wish. So they will communicate as well. They'll tap the web to communicate. So it's optimized really for different kinds of things, but that's what makes it really interesting. Once you become a little bit like the spider and you live in this web and you listen to it, hopefully down the road we'll be able to communicate with the spider as well. And I can talk a little bit about that later too. And actually I showed some preliminary work tonight on using these kind of spider sounds as a way of perhaps speaking to the spider using AI. I think I mentioned it a little bit earlier in my remarks. We can use artificial intelligence to learn the words spoken and generate words that are spoken by the spider. They're not real words, of course, they're signals. But the methods are very similar to the kinds of methods that are used in speech synthesis of human voice, which is now quite possible. And you can generate some really realistic voices now using AI. We are trying to develop some realistic spider languages, essentially, and we'll be able to hopefully communicate with the spider and solicit a specific response from the spider, like simulating prey, simulating courtship signals and others, to be able to interact with the spiders as a human in ways that we couldn't do before.
Let's see. What insights into spider web structure or construction have you obtained from translating the webs into music?
Yeah, so one thing that we've learned is that just generally from by studying the web and being able to look at the data is that we've been overwhelmed with the amount of data we have. These webs are very complicated, and so when you just use visual inspection, it's very hard for your eyes essentially to pick up all the different details. So having the sound as another backdrop to information allows us to understand a lot better where interesting regions are on the web. What I mean by interesting is the regions that are very ordered and organized, the regions that are very random, the regions that are almost empty. As you were asking earlier about the way the construction works and the sonification works, is that we assign these individual fragments of silk threads certain physical properties and then frequencies and make them audible. So by listening to the web, by wandering around, we'll be able to pick up certain regions that are very interesting, and then we can use these regions for further analysis. And one of the things we have looked at is one of my former students has created some designs for composite materials from these web geometries. So you can kind of pick a certain regions of the web and extract it and maybe develop new synthetic materials from that. You can begin to look at the way these webs are actually constructed. So that's the most recent work has been actually in observing the spider and building the web. And by doing this, we learn the actual mechanism by which the spider is able to act as an autonomous 3D printer. I opened my remarks by talking about the 3D printing idea. Right? And so this is really something that, even though we've made a lot of progress as humans, we're still relying a lot of times on support material. We're basically adding some scaffolding. Just like when we build houses, we have scaffolding usually there that we remove at the end, and in 3D printing it's very similar. So we have these scaffolds that we need to build so that we can actually assemble a material. And spiders, of course, don't have that, right? They're autonomous 3D printers, intelligent, meaning they take the signal from what they've built and they don't even see it. They mainly sense it through the vibrations. And decide where to put the next material piece and build the web. They're able to sense the integrity of the web. If it's damaged, they can repair it. So they have a whole different relationship to the structure they built, in that they're actually part of it. They live in it, and the web becomes part of their body. So these are some of the features that are geometrically very complex, but are very, very easily accessible through the ears. The ear is very good in picking up patterns and seeing differences, and you can think about it as sort of a foreign language that we're speaking. And if you just look at the letters, it doesn't quite make sense, but sound audio is a universal way of understanding information beyond a lot of the information that we can pick up by just looking at the geometry. Right? So essentially you would look at pages and pages of data, or maybe pages of images, and you wouldn't be able to understand patterns or relationship. Now, looking at it with the sound through the vehicle of the sound is a very natural way of understanding the information.
Can you tell us a little bit more about the 3D? Did you say composites?
Yes. So one of the applications was to because these structures of the web, of course, remind us of truss structures that are found in architectural designs, like the Eiffel Tower, or maybe in bridge design. And so one of the students mentioning has created an idea to use parts of the web, develop a design for a footbridge. That was her master's project to develop this. And so you just basically use segments of the web that we've identified to be particularly interesting, and created a model of that and simulated whether this could be developed into a bridge design. And we were hoping to build that bridge one day. So maybe once COVID is over, we'll be able to prototype that at MIT somewhere, and it would be really fun to try that. So there's there's sort of the actual literal translation of the web, but there's also these translational applications where you can take the geometry, the cue of the geometry, and then modify that and use it as a basis for something that may not be built out of silk. Right? So obviously the footbridge wouldn't be built out of silk; it would be built out of wood or steel or maybe some plastic. But the geometry, these features that we've identified through the sound analysis, are something that we can translate directly.
You'd have to seed it with some spider colonies.
Yes, well, exactly, and I think ultimately we in a more in the vision for where this work is going, and generally the work in my lab is we're interested in looking to nature not only as a way of understanding how nature does things and how we build how nature builds really incredible materials, but also changing a little bit of the paradigm and how we think about materials. Like now, materials are essentially built and made, and then you ship them off to the consumer or you build a bridge out of it, or you build an airplane or something like this. And you have to kind of bring it back into service to inspect it and to repair it. And what we learn from species like spiders and really pretty much any living organism is that, of course, the construction of the material and the maintenance is built into the living organism itself. And I think this is a fascinating direction where we think the chemistry, of course, plays a very fundamental role in understanding how materials are created and how they break and how they function. So by going to the level of molecules, as we're doing in our work, then building up the material structures from the molecular scale all the way to in this case, the spider web scale, we'll be able to intervene at functional levels in a much more intricate way. And by endowing these systems with intelligence, here we have natural intelligence, the spider, we can imagine creating a synthetic system that will mimic what the spider does and sensing the web, repairing the web. And so you can imagine, future bridges or airplanes or structures might have some of that repair mechanism built in, and you wouldn't build something and then wait until it breaks, but you actually continuously repair it and becomes a living organism. And in addition to that aspect, I think we're very interested also in thinking about how far we can push biomaterials, right? So we have, of course, always used biomaterials as humans. Wood is an example, but a lot of these biomaterials haven't been able to match a lot of the properties we have in engineered materials like steel and concrete and materials like this. And so we're trying to see how far we can re-engineer biomaterials by essentially reassembling the molecular building blocks into something that behaves almost as good or maybe better in a lot of cases than materials like steel. And the reason why we're trying to think beyond steel or concrete, conventional concrete or steel, is of course because these materials take an enormous amount of energy to produce, right? So they produce a lot of carbon, need a lot of energy, but for example, concrete actually, during the creation of concrete, during the setting and hardening of concrete, the chemical reaction itself produces carbon. So you have the carbon footprint basically from the energy needed to make the material. And then when you apply the material, you have carbon emission as well. So looking to nature in trying to see, can we go beyond just using wood out of the forest, basically? Can we re-engineer these materials and rebuild them molecularly? Spider silk is an amazing example. It has the strength of steel, toughness far higher than steel. It's a material that's very expensive right now, and the spiders make only very little. That's why it's such an efficient material. But if we can make it on an industrial scale, we can make it in large volumes with less price, becomes economically feasible. I think we have a really exciting opportunity to create materials that are biocompatible, that have a lot of these living structural features embedded, and that might actually be much more sustainable in the long term than current material technologies. And so this is an area I think where chemists, chemical engineers, material scientists, engineers of any kind, and anyone really working in this field has enormous challenges and opportunities ahead. So we're very excited to contribute to that direction of research.
All right, thank you very much. It's been quite fascinating hearing about your work. The archived version of this session will soon be posted at www.acs.org/ACS Spring 2021 Conferences. Please join us for our next press conference tomorrow at 11 a.m. Eastern. Thank you.